Good morning, viewers. Hello and welcome to Tech Simplified TV and a very warm welcome to the Semiconductor podcast. We are back with another exciting episode, and today our guest is a very dynamic and energetic, a very, I would say, a person who has a range of experience starting from corporate to research to engineering training, and you can find him in almost every prominent conference of this country. Professor Amlan Chakrabarti.
Yeah, thanks,
Thank
Munmun. Thanks, Munmun, for this brief introduction. Yeah, thanks. Please go ahead. Yeah.
Get done. And I would say my introduction is quite shorter with respect to his vast experience. I would request everyone, those who are my viewers, please go to his LinkedIn profile and just check kind of experience a person can gather, a kind of portfolio he has. I cannot say it. Right now, he is serving as the director of A.K. Chaudhuri Institute of IT in Calcutta University. He is right now visiting professor of Kharagpur IIT. He is connected with IIT Delhi, where he is not connected. Few week back, he went to VLSI. He is a regular visitor there, and he is one of the prominent personality in right now who are working in quantum computing in India. And I know him for last 15 years. That time he was younger. He was very energetic and dynamic, and with time he has not slowed down his energy and he has become more dynamic. What is the secret of your energy, Omlanda? That is of the book question, because that every time that I just wonder how you manage to do all of these things. So many work, so many conference, so many engagement. How you manage?
Yeah, the question is that you have to be on the things. That means at present you have to know the things. The things are so fast, moving in terms of technology. Any domain you say, right? If you don't actually be in the places, listen to the experts, try to work with them, okay, right, and try to plan something, right? You are lost out. So obviously there are time limitations. There are limitations due to the assignment that you have, but I try to don't extend everything too much. Try to finish the work as it is required within the time, so that I can save the time for some work which can progress me.
Okay.
Yeah.
It's a question. That this question was quite for a while in my mind, that one day I will ask Omlanda that what is the secret of your energy. But by the way, we will start with your journey, because you have started from corporate. You have worked professionally
Yes.
in a company, then shifted to research, engineering, training, research, and now completely with so many institute. How this whole thing shaped up in your life? We will start
Oh,
with
this
your
journey. Yeah, when I look back to this journey, I also sometimes think that from where I started and where I still I am, right? That obviously the thing what I try to do is that what suits my thought process best, right? What suits my uh, my ambition as well as my uh, technical expertise best. I should do that. Okay, so what I did is that, as you know, that after my masters in electronics, I finished in the Science College campus. Right, I got two job offers. Right, one job offer is obviously an OrCAD subsidiary in Bangalore, and one job offer was in Siri Pilani. Okay, Siri Pilani, I was selected as a scientist at that point of time, but I didn't join there because it was a little bit long process, and the offer from Bangalore was very tempting. At that point of time, you can just understand 1998, right? That means a person having electronics background getting a job in EDA, okay, right? From the technology point of view, was um, very fascinating for me to learn the new things in industry, and it was a good experience for me in industry, almost 1.5 years. Okay, at so what I learned in the industry at that point of time, we were working with the data sheets of electronic components, and we were developing the libraries for the OrCAD. Okay, we had the capture and the footprint. Okay, okay, capture was the schematic, right, and footprint was the back end of that, by which you can actually take the component back into the PCB. And I learned lot many things which were not directly though our electronics teaching at University of Calcutta was very good compared to the other institutes, but obviously the data sheet, understanding the data sheet, understanding the components, electronic components was not taught in any particular institute at that point of time. Okay, so I learned that, right? What are the electrical characteristics, mechanical characteristics, and how it gets into more importantly a EDA tool, right? EDA tool is an abstraction of an electronic component, and then it gets to a mature design. Okay, but I understand that process flow. But I was pretty lucky that at that point of time, OrCAD was just shifting, okay, from the component on the PCB space, okay, the components on the IC space, and I was one of the core members of the team who were being taken due to my performance, obviously, okay, were taken into the developing the VHDL library, okay, OrCAD. Okay, right, and that was a fascinating experience because that point of time, okay, 1998 in India, right, the knowledge of VHDL and the logic synthesis was pretty less. And then when I came back again for my study in radio physics electronics, okay, then when I came back, it helped me, and I started taking small lecture courses, okay, for professional institutes. When I was studying MTech electronics in radio physics department of our university, then I started taking course, I think in the last year of my course when the project was going on, the courses at the university. Yes, okay, that gathered me experience that, hey, that means the new technology, learning new technology, and then actually training the aspirants in that is really a very good motivation. So that journey motivated me, that means from the industry knowledge what you have, right, you can actually take it back, okay, to the students or to the young learners who wants to get into the industry. And then it went on. Then I thought that, okay, I mean, if I am teaching, I need to have a PhD, I need to do good research, and then went to Indian Statistical Institute. Okay, there were some good senior researchers whom I was already connected. I approached them, and I was lucky to get the supervision and get the support of Professor Shushmita Shurkole of SEMU unit of ISI, who is obviously an illustrious figure both in teaching and research. And I was very few of the people, right, that point of time in India, right, who were doing research in quantum computing. And from my EDA background, Shushmita said me that as you are an EDA, you know algorithms, you know how the synthesis and the design works. So why don't we try to work out on a new EDA which will be for the quantum computers, right? And I submitted the thesis, which was architectural design of quantum computers, which actually laid some foundations of the logic synthesis, what we really see in Qiskit and all other tools. Okay, right. Those thought process, okay, were generated. Obviously, there were pioneers already in that particular domain. Like I remember, Maslov was there, University of Waterloo. J.P. Hayes was also was there a bit. He was starting on that. Okay, there were good researchers, but very few good researchers were going on in very top labs of the okay, that means all over the world. And I was very happy that I did a research which was very progressing at that point of time. Then I went to Princeton for my postdoc. Okay, right, learned fascinating things from my two supervisors, Professor Neeraj Jha, okay, from Department of Electrical Engineering, and Professor Margaret Martinosi from Computer Science. We developed, as a postdoc lead at Princeton, we developed the first quantum computing compiler, which is still in the Princeton. It's called FTQLS, Fault Tolerant Quantum Logic Synthesis, which was a tool by which you can come up with a very functional description of the circuit that we do in a VHDL form. It was called quantum language, right? We developed a quantum language, and it generates a netlist, which was specifically for technology. So what comes, you describe a function in the quantum, okay, that is using a quantum language, quantum assembly language, and then it generates a circuit description of the netlist in terms of the different quantum gates and technologies, and that that's slowly taken over by by the modern tools what we see today. But I am very happy to say that the one of the first quantum simulation simulator generating the quantum circuit net, this was developed by Princeton, and I took a major role there, right? And I learned not many things for my almost 1.5 years stay at Princeton, and then came back to my country, right? My position was already being there in the University of Calcutta, right, as a school of IT. I was already joined around 2006 when I was doing PhD in ISI, right? I was lucky to get selected in the position as a lecturer, right? And then I went into multiple things. I got very good projects in the if we go for the from the EDA, then I also moved to architectural design of SoCs, where we worked with very good global projects. That means my really regards to Department of Atomic Energy and Department of Science and Technology, who actually funded very very strong projects, which were called the CBM Fair projects, which was running in the GSI Helmholtz lab at Germany, and CERN Alice project, which was running in CERN Geneva, right? And my team was inducted with a team of physicists from various institutes. Right, my team was basically develop the hardware or the firmware for the data acquisition chain. And again, I will tell you that we are the first group in India, along with the experts from UCC Kolkata, and I think there was also a foreign university which was also helped us. We developed the first firmware for the gigabit transceiver, which were used for the for the data acquisition chain of this nuclear detector experiments. And that was published, I think, in 2018 in the ITP Transactions of Nuclear Physics, where we were the first of the group. And then it goes on. We worked with multiple DRDO projects on hardware accelerators, on crypto hardwares, worked with Intel, right, on accelerating the crypto, worked with TCS on multi-core scheduling of real-time tasks, right? And then went on and on, right? And obviously quantum computing started in 2017 again in India, though it was a little bit back end for me to do quantum computing coming back in India, but I was doing at the back end with my supervisor, Professor Shurkul, and a couple of my students. But strong quantum computing funding and quantum computing activities initiated again in India in 2017, and now we are doing very good for the National Quantum Mission, connected with a couple of the groups in the research, right, with CDAC and all these groups, and we are trying to do some good contributions there also. So it was a journey which started from deep understanding of logic and maths and graph, right, and now it is more towards incorporating AI and quantum into the various application space and critical infrastructures. Yes.
Amazing journey you had, and it's almost like a spiral. It's just become bigger, and in every round it's becoming bigger and bigger, and I hope that continues for coming many years, because we really need, at this point, we need your guidance, and we are really fortunate that we have you in this state, in this city, because hope sooner or later we will get some attention from Meiti and get some more thing will happen here also, because Kolkata has much more better infrastructure compared to many other adjacent cities.
Yeah, we have some of the best students of the country, right? You are also from Calcutta, right? We have the best students from the country. I know that the institutes of Bengal, right? Especially Calcutta University, Jadavpur University, IIT Kharagpur, IST, Shibpur, ISI, right? NIT Durgapur, right? Jalpaiguri Government Engineering College. These are the institutes which has that was, and many more, which I didn't mention, right? Which have actually produced gems, right, of the country, of the world. Yeah.
You rightly said that our what we the kind of syllabus we had, and kind of that time we also thought, are we at par with the other institute? Much later we came to understand that the kind of strength we have from those days, it's not parallel, rather much better than many other institute. Yes, it's true, because even today
Our fundamentals are pretty strong. That's the core reason. That's the core
Whenever
reason.
you are studying semiconductor, you have to understand
Yes.
solid state physics. And who can forget Professor Dhor's class, Shunando sir?
Ah,
His
perfect.
SB
Professor
class.
Dhar, DP Ranjan, DRC, right? They're
Yes.
have
So
phenomenal
we
teachers.
were fortunate. It's a star-studded thing we
Yeah,
had. So that time we didn't have much exposure. Later came to
that's
understand. Yes, what we have got is we are really fortunate uh, to have
right.
these classes
Perfect.
we have. So you just started, and I mean, when you started, it was just your supervisor you took you to this quantum computing because it was too early to get. I mean, or the just interest you just got into it. Now it's getting a huge traction in this country. And when you did it, you are, as you mentioned, that you were among there are few groups across globe who were working in the same thing. Or is it that you were connected to ISI, which is one of the premier institute in this world, actually, in Kolkata, but it's one of the premier institute. That's why you got that chance. I mean, how quantum computing so early? This is the
Yeah,
thing.
yeah. So yeah, it's a very good question. So obviously, as you know, that many of the seniors of ISI, right, that point of time were actually the seniors from University of Calcutta. So it was a easier for me to approach them, okay, for my PhD. And when I thought that I will be doing PhD, right, ISI was my first connect, right. Uh, okay, because I was fascinated with one of the professors. I'm not. Yeah, I can name also, right? I was fascinated with the work of Bhargav Bhattacharya, right, that point of time. Though it was not in the same way. I will just tell the roundabout story if you give me 2 minutes. So I was presenting my master's thesis project at radio physics electronics, right, when there was a phenomenal professor from Jadavpur University, Professor Devidas Bandopadhyay was our external expert. He was a phenomenal professor. He knows the CMOS, I think the MOS transistors like a god, right. And so what was my project? As I was from Bangalore, I know EDA tool, so I updated a tool which was there in radio physics, which was built by the radio physics department for, okay, from research point of view, but it was not on the present tool flow, right, because present tool flow, okay, right, what I learned, you cannot have you need to have an integrated flow, okay, from your okay, from your design entry, okay, to your visualization of the design. So that was not there in the tool. It was a fabrication tool where you can actually look into simulation, fabrication sim, where you can look into a semiconductor. You can give the different types of impurities, okay, dopants, and you can see how the characteristics changes, right, in a simulation window. So but to do that, you need to go with several chains of files and several chains of blocks. So what I did, I integrated them. I had a very good programming uh, uh, okay, knowledge at that point of time in working industry. I developed a C++ based front end tool, VC++ based front end tool, right, which can run that previous tool at the shell, right, take the result, right, instead of going to another tool, okay, right. We developed an internal file process and that spine based interpolation technique to draw all the curves and generate all the visualization. So when I showed that in the project, right, I was very lucky to get the highest marks in this my master's thesis project, right. And Devidas Babu was very, 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 very excited with that particular work. And then I went to Devidas Babu in Jadavpur University, said, I want to work with you in my research. He said that, Amlan, the work what you are doing is best suited for Professor Bhargav Bhattacharya, whom I know previously also, because Professor Bhargav Bhattacharya was more on the okay, simulation and designing part, and Devidas Babu was more the devices part, okay. So I went to Bhargav Bhattacharya. Bhargav Bhattacharya connected him in email. That said, I want to work with you as a PhD. Then Bhargav was in a 1-year sabbatical in US. Okay, so he said that means I am referring you to one of my very, 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 very good student, Professor Shushmita Shurkole, who was in ISI at that point of time. That was obviously not a professor at that point of time, but she was very, very, very promising and very, very accomplished researcher at ISI at that point of time. So I connected her. And then she said that means that I always have a knack to do something which most of the people doesn't okay, go forward. That is a good or bad for me, I don't know. Okay, right, I have a tendency in my life to do something which is, okay, which is not a very common thing, which I have to really work hard to get it. Okay, so I said Shushmita Di that let's try to. That means we can plan something which is good. Shushmita Di also said that he had some US connects at that point of time. Okay, right. She said that means we all have a physics background, right? So we have done a bit of quantum physics and electronics also. We have learned a lot of quantum electronics. Okay, Shushmita Di has a confidence on me that I understand quantum physics and quantum electronics. Okay, so she said that means you will be the good person to start the work on quantum computing in ISI, right? Which is first of the work in the in the computing domain, and that's where the started. So it was a trust of Shushmita Di, right? Who trusted me that at that point of time with very very less resource and very very less tools in that domain. No tool actually. We all developed the code on MATLAB and C++, right? Now the students actually don't do that. They use all the tools which are available in IBM platform or other platforms and do it. But Shushmata Di was confident on my computing ability, confident on my quantum knowledge, right? And she trusted me that basically I can do that, right? And she was a fascinating supervisor, right? And right, she helped me a lot to understand that what is a good research and how we should start formulating a problem and how you should actually design and ultimately implement and ultimately analyze the results coming out of the problem in a very thorough way, right? And that helped me to guide the research students who have graduated from my group, right? I tried my best to follow the guidelines that Professor Shushmita Shulkole taught me during my PhD course.
Okay. So it's almost 15 years already spent. You started working on quantum computing
Yeah,
and
20
that.
years, 20
So
years. 2005, I started my work, and
so
2025 gone.
now in India, it's getting a lot of traction. In National Quantum Mission is there. Still,
Yes,
when you look back, because you have that rare experience of first, being the early bird in the domain, you have
right.
made those tools which were now available. That time you had to do it, make your own tool and then work out with it. This kind of
Perfect.
rare experience hardly people get. And yes, those days were really tough for you, but you have that vision which many people they don't can get. So what do you see now the key bottlenecks in making quantum computing more practical from hardware or CAD tools and algorithm perspective? What is where we stand now in India? Where we stand if we compare, because it's very critical right now. We should analyze where we stand because we are competing in good way or in bad way. When ecosystem is trying to be resilient, it has to compete with the others well established ecosystem. So we that kind of retrospect our position and analysis, I think it's very important. Since you are an expert of the domain,
Yeah,
tell us.
yeah. So, so the plus point, the advantage of India is that India has a very good understanding of physics, maths, and electrical engineering. Right. That means these are the three things you require. So quantum computing is a very hybrid type of technology. Right. It is obviously if you look into semiconductor also. Right. It is also a hybrid, but semiconductor technology is so old now. People in computer science can take packages of electronics and can design the tool. Okay, they will take the technology library just like that, and they will do the optimization of the things and all these things. But quantum technology, you have to understand, it is still at that level. So if I want to work with the quantum technology, quantum computing, I have to know all these things at least at this point of time. Okay, maybe after 5 or 8 years the packages will be so strong. If you are doing computing, you don't bother about much about the physics. If you are doing physics, the computing automatically comes, those things will come up. So that's the advantage of India, because India has a very good physics, maths, and electrical engineering institutes, right? So the opportunity of the Indian researchers to contribute in quantum computing is very good, and we have really actually the Bengal, the state of Bengal has actually that means generated good quantum computing and quantum technology outputs in terms of research. Okay, but as you said, right, if you want to competitive in the international world, we have to make the products. Okay, because products which actually take you to the market and give you the recognition. Obviously, research is the backbone. Research, that means unless you have research in the technology, you cannot develop products. But ultimately, we have to come up with our own quantum computer, which is a product, okay, which we can use, and by which also government of India can actually make this technology available to the other countries, right? And we can earn some good funding through that. Okay, so in that terms of technology, right, we require, okay, DST has taken a right decision that to form a very, so when you say it's a mission, it means that it's a very high priority for the government of India, right? And that priority has been established by the establishing of the National Quantum Mission. Okay, but in terms of the engineering, right? Engineering, the challenge of quantum computing is that when you go from smaller number of qubits, okay, to the higher number of qubits, right? The integration of these qubits, okay, right, requires lot of engineering advancements, and the engineering advancements are still a little bit volatile. It's not freeze that, okay, that means if you want to do 100 qubits computer, this is the only direction. It's not like that. Okay, the different research labs are trying out different options and trying to optimize this in terms of control, right, in terms of cryogenics, right, in terms of error. Okay, so the qubit technology is now very available, but the only thing is that when you scale up to large numbers, okay, right, what is the cost, what is the latency, and what is the error? Okay, minimize it. What level of minimization you can do at maximum? Okay, right, still it is going on. Okay, so at this point of time, the good point of India is that India, like some of the labs like IC Bangalore, TIFR, okay, TCG Crest, right, they have the small capacity, and CDAC also starting and thinking about bringing a qubit, a good number of qubit infrastructure. Recently we had a lecture coming from the DST, okay, Secretary Professor Karindikar, where he said that the target of this particular mission is almost 100 qubit quantum computer will be there in India. Okay, right, with the efforts of all the teams, and ultimately it is not only the hardware, you have to develop the stacks, the applications, and the high performance computing on that particular top of that. Okay, so I think that means India, I think within the next 2 years, right, that as I believe, both in terms of research, right, and some of the startups are already being funded, okay, by the government of India, okay, to actually get the research to the product level, right, and they are doing fantastic work. QAI, Q New Labs, they are doing good work, right. So what I believe is that the next 2 years is a test for the Indian researchers and the Indian companies. Okay, next 2 years we have an immense opportunity to actually visualize or to actually come close to the 100 qubit quantum computer, right? And if we can do that, maybe I'm telling 2 years conservatively, but maybe it can be 3 years also. But within a short span of time, if I see if India can hit a 100 qubit quantum computer on the developed by the Indian researchers, and we can exploit that for the various applications, critical applications, right? And that I have a very strong hope. And I think we will do it, right? And so that's why I will take a very positive note that India is on a very good track. But having said so, we shouldn't just think that all of the rest will do. Okay, right? We have to work together and join together, and we have to all contribute towards this particular landmark of the Indian computing, and I think that it will be done.
Okay. So you said 100 qubit quantum computer. So in other countries, I mean, it's already available from any other research group, any other country.
Yeah. So IBM has 100 plus qubit chip. Okay, right, and they are looking towards a multi chip. I was invited by IBM Watson in last year July. I visited their lab. It was a fascinating experience. But they are on the process of they will be integrating multiple quantum chips, Okay, right. Together, that is again another technology, how we integrate multiple quantum chips, which are 100 plus qubits, and make 1,000, 5,000, 10,000 qubits. Okay, right. That's a second level. Okay, how we integrate all these chips. So if you compare some of the top industry standards, they have achieved 100 plus qubits, and they are in the process of integrating this 100 plus qubits to make 1,000 plus qubits, or multiple of 1,000 qubits, and offer it as an processing engine. Okay, so so that step is the next step. Once we achieve that, we can do a 100 qubit chip, quantum chip, or QPU, right? We will go to the technology where we can. Okay, but that technology, I think, is not so complicated as making 100 qubit chip itself. Okay, once we achieve the 100 qubit chip, we can actually have the multi-core qubit, the multi-QPU chips. Okay, right, and we can have a back-end very high-speed optical quantum communication to interface all of this. Okay, right, and we can come up with this multiples of 1,000 qubits, and we can hit the 5,000 qubits mark, where quantum computing is promised to supersede classical computers.
Okay. So I have two more questions regarding this, just to get a real life perspective of it. Like,
Mhm.
what is actually the typical cost of making a 100 qubit quantum computer, and where it will get its typical usage in which applications? In all applications or in specific?
Okay, so in terms of cost, I think 100 qubit quantum computer, it depends on, that means what is the level of accuracy you are trying to do. I think it will come around few hundred crores, okay, for a 100 qubit quantum computer, because okay, that's the present. So we can expect that at least for a 100 qubit quantum computer, we require at least okay, some few hundred crores. Might not be hitting 1,000 crores, but few hundred crores we will require, okay, for that. Okay. In terms of applications, it's a very good question. So quantum computer helps in the domains, right? Basically, if we just go in a very thumb rule, quantum computers helps on those problems which are basically search problems. Okay, because any search problems looks over a large space. The search problem is challenging if the search space is very, very large, right? And you have to find some of the samples in the search space which matches your criteria. That's a search problem, right? It can be one sample, okay, right? If it is a minimum or maximum, but many of the times we try to find optimal, okay, which is actually closer to this. Sorry, I have to switch off the power. Yeah, so closer to this. Okay, closer to this minimum maximum, we can actually go into 2, 3 multiple points. So, okay, so what happens in a quantum computer is a quantum computer can actually present the search space in a less number of resource, and can functionally explode the search space in parallel. Okay, right. So many of the large graph algorithms, okay, many of the image processing algorithms, right, many of the optimization problems, right, can be taken care in the quantum computer in a much faster way or less resource than a classical. Apart from that, quantum computer inherently goes with the quantum Hamiltonian function. And that Hamiltonian function, okay, that understanding the Hamiltonian function or simulating the Hamiltonian functions are the key for the molecular research, be it drug design, okay, be it finding new materials, right? It is actually how the Hamiltonian behaves, okay, right? And quantum computer, and as the quantum computer has an inherent Hamiltonian, you can always model the required Hamiltonian for simulation in a quantum system. You can map it in a quantum system, and quantum system can actually just simulate the Hamiltonian, okay, that means, and can give you the useful results, which are very much important, okay, for the applications where we have deep science, okay, like as we said, the drug design, as we said, the materials and drugs. These are the key areas now in the development. If you look into defense, okay, right, if you look into health, right, they actually look into materials, and for health science, for agricultural science, okay, right, for food science, right, everything is basically based on this molecular analysis. And at the present classical simulation domain, we can, I'm not expert on that particular, okay, chemistry or a drug design, but I have known that it is only we can do something like 100 level of simulation, and we have to close it because we don't have resource to do that exact simulation, which will be almost 100 or 1,000 times what we do now, right? Using quantum computers, we can do those simulations, the complete simulations of of those domains, right? And that will be very much helpful for the society to generate new drugs, to generate new materials, to generate to find out the efficiency of a interaction of a pest, or of a plant, or the soil components and the plants. So all these things will be far well analyzed when we have that quantum computer based analysis.
Okay. I When you are saying the about the typical usage, so as much I understand, yes, defense could be a very that. I mean, I was about to think probably that could be used in defense. Another thing, when data is huge, like surveillance kind of work could be done with it very
Yeah, sorry, I missed the communication part here. Communication and sensing. These are two other parts also. Okay, so surveillance is basically sensing. So quantum inherent as they work with a minute change of energy. Okay, so the smaller fields which were not being detected by the present sensors, smaller variations in the energy field which are not detected by the sensors will be well detected, and you don't require any external energy, okay, to actually come into play, right? The quantum state can inherently change with the interaction with the very low amount of field which is available in the environment, and those change of states will be measured at the sensed energy values or energy levels of the environment, and that gives you quantum sensing. And similarly, quantum communication, quantum has a very, very important thing, that you can have a lot of the basis represent choice of the basis when you send the data. Okay, so you can have different bases of sending the data, right? And if you have to decrypt, or if you have to capture the data, suppose and if you both have to measure the data, and you have to know and you have to know the basis. You cannot do it, right? You cannot capture the basis, because that is the thing which is being settled by the sender and receiver very randomly. So instead of making the data random, okay, right, we actually make the measurement basis random in quantum, which makes a third party, which is an Eve, right, to capture the data impossible. And if it tries to capture the data also, the amount of error in the channel will be so high. Okay, so automatically the parties will know that there is an attack. So what happens in the quantum communication is that that means it helps to faster detection of the attack, and it's almost impossible to capture the data, because it's not only the polarization of the photon what you need to know, right? You also have to know that on what basis this polarization was generated, right? And that is completely random, and that is the difficult part of decoding a quantum state, okay, without incoherent with the source.
okay. So it's an asset for a country who is really serious to protect itself. It's not only other usage, or also very inevitable for this kind of work. Understood. So when power consumption is a very critical thing when we talk about the computation level, high computing and data center. It's the first thing is that power consumption. So it's a critical challenge. So how the concept like reversible logic and low energy computing that can help in this domain? Since
Yeah.
you are expert of computational work and
Yeah.
all.
So there are two parts of power. So if you only look into the computing power, quantum computer, see, a classical computer has that means has a pipeline. So it actually reads and writes on the memory in the various stages. That there the clocking happens, which actually flows the data from the initial fetch to the execution. There are different stages in the 4 or 5 stages in the pipeline. So each of the stages needs to be clocked. which is an energy consumption, right? And each of the stages you are writing on a write buffer and reading from a read buffer. Okay, so which means that you are doing read and write on the memory. So which means that you are consuming a good amount of power depending on the number of bits you do in each of the process, each of the steps. Okay, but in quantum computer, the advantage is that you are not having this pipeline. You have the qubit states which are initialized with your data, which initialized. That means you have the initial qubit state mapped with your data in some form, in the phase and the amplitude, right, of the qubit represents the data values. There's a quantum encoding which maps your data values to the amplitude, to the states, to the basis of the qubits, and then you only transform these qubit states. You don't do anything else. You don't do the multiple stages of in and out, right? Multiple stages of clocking. So you actually you modulate these states, and these are the transforms which happens in the qubit space. And ultimately, you again measure the qubit states in some way and try to get the result. So it's like an in-memory computing. Okay, right? You actually define the data, right? And the evolution of these quantum states is the computation. You will start with a state of qubit, and you will end up through the evolution process. You will end up with the sum states of the qubits, right? Which is your result state, and then you can measure. Okay, so those states, those intermediate blocks of read and write and the clocks, right, are not there. So obviously, you only require energy to actually run those transformations on the qubit states, and that's the energy. But having said so, presently you have these control signals coming from microwave signals, right? And microwave oscillators require some powers, okay, to actually generate the RF frequency for which this qubit resonates and do this state transformation in terms of phase, okay? And also there is a cryogenic, okay, which needs to make this qubit system super cooled, so that the interaction with the external environment is almost zero. It only interacts with the RF field which is passed to the control signals, not with other energy fields. So those are the things which are now required to actually drive the computer system, but not the actual computing. Actual computing is very low energy, but to maintain that scenario, you require the things. So now the research is going on that how you can bring the control closer to the qubits, so that you require less energy of the microwave signals, okay, right? And people are also working with the cryogenic electronics, where the cryogenic requirement of this will be reduced and optimized to a great level, okay? And all these things are going ahead to actually make the support system of quantum computer also low energy. Presently, if you see only the computing energy is very, very low compared to the classical. But to make the support of this quantum system stable, we require all these extra things in terms of cryogenic and also the microwave, that is high energy microwave pulses, okay, to control those. Provided the engineering matures in that domain, right? Okay, right, we will have a low energy computing.
Okay. Yeah. Okay, that's yes, I have seen those cryogenic system.
Yeah, those are called dilution refrigerator. Okay, yes. Which actually controls this. Yeah.
Many people. One of your students, Uday, he shares that we are connected in, so I get to see all.
Okay. Okay. Yeah. We are trying our best to ultimately come up with a fabrication of the qubits. We have a very good the designs of these qubits at present in our lab. Okay, that Uday is the master student in my group, and we're also working with DRDO and CDAC, right, in 2 capacities on this particular work. But now we are looking for a fabrication partner. Okay, we don't have that amount of funding to fabricate our design, so we look forward. This may be a good, good platform for me to also to convey this to all the viewers, that we require support for fabrication, right? If anyone is interested to work with us and support the fabrication, we will be very happy. And we need to, unless we fabricate and characterize the qubits, we don't know what are the real issues in our design, right? We have done the design verified and visualized in all forms in the simulation environment. But as you know that these particular device level simulations are only get satisfied when we have a fabrication of that and characterize the fabrication, and then we know that, okay, we are trying our best to do that in the next level of our research, right? And we're looking for collaborators for that. Yeah.
Okay. Hope you get your collaborator. In India,
And,
is this facility available, fabrication and all, or we need to collaborate with some foreign institute?
no, there are actually the goal of National Quantum Mission is also that to develop a common facility for fabrication of qubits, right? And there are some industry facilities also available, okay, right? Who can offer us, but still, I think the most of the things which are being working in India in terms of qubits, right? There are few which is being fabricated outside our country.
And since you are saying it's need to get fabricated, so in which material it's what is the basic
These
material?
are basically superconducting. So we have this aluminum. Okay, we have this aluminum, and we have an oxide layer. Okay, which is required. Okay, right. And there are some. Recently, I have seen a work from Oxford. That means, and I think Microsoft also presented this in one of the what Microsoft also is doing. Doing the fabrication of their QPU. Right, they are using different materials. There are different materials which needs to be done. Okay, there are different materials, superconducting materials. Basically, these are okay, right, which we need to use, right, and we need to have an insulator, okay, which forms this coupling of a capacitor inductor equivalent, electrical equivalent, right, and which defines a transmon. Though there are other techniques apart from transmon devices also. There are other techniques of this superconducting qubits, but we are mainly focusing on the transmon devices for superconducting. Yeah.
Um, you have also worked with FPGA based embedded systems.
Yes.
So, and this, based on your experience, where do these reconfigurable platforms stand in today's and tomorrow's semiconductor landscape in coming decade?
Reconfigurable computing, that means though when I started my research in reconfigurable computing, people a little bit, I mean, my friends, I will not tell, my friends just said me that, hey, you are moving from your real design to something which is mostly firmware, right? But I was pretty confident at that point of time. I developed my FPGA lab at the School of IT, University of Calcutta at 2009. Okay, obviously with a good support from Xilinx, I should recognize their help. Basically, the CG Corel labs in Bangalore, they helped me a lot. Xilinx also donated me a lot on these, and later Intel came up with their own FPGAs. They also gave us a donation, our lab donation for that. So these are the things which helped us. And what I said at that point of time, I thought that, see, that whatever you do, whatever fancy you do, right, ultimately that means how flexible you are, will win, right? And all of us, we know now that FPGA is so powerful, right?
Yes.
FPGA previously, when we used FPGA, it was just a prototype design in FPGA, and then you go to ASIC. But now it is not like that. FPGAs are now SoCs, right? We have the FPGA based SoCs, right? We have developed an FPGA based SoC jointly with IIT Hyderabad for one of our defense projects. And it is a very, very powerful FPGA, right? It accelerates the deep network algorithms. We can customize it. We can update it. We can update it in the runtime, right? What we work with TCS. Okay, my student Dr. Shangit Shah, I don't know whether he is here. Dr. Shangit Shah graduated from my lab as a PhD, and he's an assistant professor at University of Essex, UK now. Okay, right? He did very good work. Okay, right, where we showed that how you can use the FPGA cores, right, for dynamic scheduling of tasks. So dynamic scheduling of tasks, right? As I also have a strong background of algorithm, I believe that FPGA is the master. right? If you want the dynamic scheduling of task, okay, right, you can just do partial reconfiguration, okay, right, within a shorter latency. Full reconfiguration is a larger latency, right? You can play with the reconfiguration strategy, and you can play with the mapping of your task to the IPs, okay, right? And you can any point of time, you can, if the space is still available, right, you can customize any IP in your space. So any dynamic environment, right, which requires that, which don't have a static IP requirement. And we also work with Intel. In Intel, what we did, I don't want to disclose it because that was a product level development.
Sure.
What we did is that we tried to look into that, how multiple FPGAs can be integrated in the cloud. And our focus was, when we have the multiple FPGAs integrated on the cloud, okay, finding the malicious one is hard. Okay, right? In cloud, you have the integration of a lot of, so we tried to make a sort of a plan or an algorithm or strategy, okay, right, which will try to make your FPGA on cloud, okay, very well done, with a security cover. And that student is also a faculty of University of Cork, Ireland, Dr. Krishnendu Guho. Okay. I don't know whether he's there in this. So Krishnendu did this research with me, okay, right, during his PhD under my supervision, and now he's a faculty in University of Cork, Ireland. So we did some very good research, okay, right. And presently I'm working with a couple of students in my PhD, where we are looking into the edge, because if we are looking into the edge computing, okay, right, FPGA SoCs on the fly is best. And also we are working with one of the startups in Bangalore, R5, okay, right. If some of you have visited the previous VLSI design 2024 in Bangalore, 2025 in Bangalore, okay, right. Myself, my very good friend, Shujai from IIIT Delhi, okay, right, and Thalas, we presented the FPGA and RISC-V, and we had the first tutorial. We received the first tutorial award in the last VLSI. So I feel that if you are going for RISC architecture, okay, right, and you are looking for edge computing, right, you can do a lot of flexible things using FPGA. I'm not I'm not opposite to ASIC. ASIC is also fine. It's also a lovely technology, but I'm telling that if you have a dynamic environment, okay, right, and if you have a resource constraint, that means multiple tasks are there, and you cannot converge the resources at one shot on the ASIC due to the cost or limitations, right? You can look into the FPGA, and for dynamic environment, FPGA is the thumb rule.
Okay. So you have worked on EDA algorithm also. You started your career with that.
Yes.
And you have worked in submicron and nanoscale technologies with it. So where do you see the biggest gap between academic research and industry-ready EDA tools, and in today's perspective?
Because industry is moving very fast. That's why I try to be in the VLSI Design Conference and always meet my industry people. So as I said, the tools which are now AI driven. If we look into, I was listening to Professor Dr. Preet Banerjee also, you can say, because he was an academician also prior to his CTO in ANSYS, and now he's presently one of the top bosses of Synopsys also. So Preet Banerjee was actually lecturing in one of the conference in a keynote where I was attending, and he said that how ANSYS is looking forward to map the physics, which is a certainty. Physics gives you a certainty, okay, right? And this ML, okay, gives you an uncertainty. So if you have to model something which are uncertain, then it's a data-driven model. If you are trying to model something certain, it's a physics-driven model. Okay, so now previously simulation was physics-driven. Okay, entirely. That means you have to have the maths in the background, exact maths in the background, right? And based on the maths, it fitted the data, right? And gives you the output, which is a simulation output. Now we have understood that if you are trying to design a particular car, and if you're trying to model that how this car will work after 5 years, considering some friction, considering some okay something okay something which is not uh, okay not in that way that way you cannot think in the design time runtime. So many things can happen, right? You have to use the data driven simulation model, right? What happened in these scenarios, what were the wear and tear in these scenarios, what is the data available of the wear and tear of a tire of the 5 years run, what are the models available. So these are now getting clubbed, right? And this is what is industry are trying to do in the EDA or simulation domain. Okay, right? Trying to take this data-driven models and physics-driven models and trying to make a fusion of those. Okay, right? And these are really very challenging tasks and requires a lot of computing resources. So the first challenge of the academic institutes are if you want to generate good simulation, presently it is becoming so inclusive, okay, right? So many things you have to do, so you require a good computing resource, right? And that's sometimes costly, and that's sometimes needs a sort of a shared resource among multiple institutes, or a state level resource or a country level resource, where multiple institutes and multiple researchers can share and build that. Okay, right? In terms of the after simulation, you have the fabrication and characterization. Okay, fabrication labs needs to be given, because unless we fabricate and characterize, okay, if we only stuck in, because what is the main issue in academics is that academics are mostly stuck in simulation. Okay, there are academics who are going for fabrication and characterization also, but these ratio, if I look into the ratio, right, ratio is a skewed ratio. So I think academicians have to actually, the academicians which are doing engineering, they have to actually, in the hardware domain or manufacturing domain they are doing, they have to fabricate and they have to characterize. If you are doing in the software domain, you have to deploy it. You have to deploy it into the real infrastructure. You have to deploy into the real edge and real cloud. And you have to make a test bed. And you have to deploy it in a test bed and try to work with the industry. Okay, try to work with a startup who will give a perfect input to what is required in the test bed. And it is not you are running the algorithm in the computer with a given data and you are very happy to see that, but unless it is deployed in a real environment and you get the performance metrics, it's very important to know the performance metrics which the domain users or domain stakeholders will prefer. My performance metrics from a design point of view may be different, but I need to look into that, how my design performance metrics maps to the performance metrics what the users or stakeholders actually require. And are we going to that level in the software development? So there are two verticals. If you are doing software development or if you are doing hardware and manufacturing, you have to look into the end-to-end now from the academic's point of view. Don't just try to be self-compliant that my simulation was very good, right? It matches my theory, and so I'm very happy. In the software, okay, my execution in my standard lab environment is very good. Okay, right? I'm very happy. No, that's not the ultimate happiness. You have to take it to the real deployment and you take it to the real fabrication and characterization. Yeah.
And now about AI, that how AI is now integrated in everything.
Mm-hmm.
So coming future, or even it already been started, so how it will change or changing the way we design a system or the way we design a chip, rather, because I understand that better because I come from ASIC. I have done work in ASIC. So how it's changing, what was there and what is new now, what is the difference?
See, there are two things you have to know about AI. One is obviously you have to know about AI. What is AI? What are the Okay, what are the models, what we do in AI, what they can do. But also you have to know that, as you asked me, good question, that what is the real problem which we can actually solve using AI in a particular domain. Okay, suppose you are telling about my chip design. So that means I worked specifically with two PhD students. At that point of time, it was mostly AI, not deep network, because I think one work I finished around 2016 and one work I finished in 2014. Okay, I think some of you know Bishwajit. Bishwajit. Okay, Bishwajit, Dr. Bishwajit Patro, right? Who was in Intel, and now I think he's also a senior person, okay, around the VLSI design companies. Okay, so Bishwajit worked with me during his PhD, right? And when he was in Intel. So what we worked on a very important problem of power distribution network. Okay, as you know that power distribution network is one of the very, very important, that is very dense now, right? Because there are so many transistors, right? Power lines are so dense, right? And if you have to optimize those, okay, right? If you have to optimize those, you have to sacrifice in terms of your delay, okay, because you have to put capacitors, right? Or you have to noise. So two things you have to take. If you have to minimize the power distribution, power noise, you have to put capacitors. If you put capacitors, it becomes an area issue, right? And also it becomes the speed becomes lower. Okay, so now we have to optimize. So what we did, we tried to generate a clustering algorithm. We developed a clustering algorithm. Okay, because why we didn't train? Because the designer components getting training set for the components is so difficult, right? You can only do a supervised learning type of approach if you have a good training set, because that point of time the data from the design space, okay, basically from the big, because our focus was, can we reduce the iteration, okay, from the pre-layout to the post-layout. Okay, can we reduce the iteration? Can we actually make the noise better handled in the signal, okay, that means in the signal closure, okay, right? And iteration is reduced, so that during the placement, okay, during the routing, okay, we can actually make it very good, so that it is very, very mapped with the power distribution network strategies. Okay, and that work, we did a very good work on clustering, and we used right, that means, and we generated some sort of distance metrics, okay, based on this placement and routing and the parameters and the feature space of the power distribution network, right? And we amicably solved it. We had good publications in JOLP, and we had publications in DAP, okay, which actually worked out well for his PhD. Okay, but the challenge is that in the VLSI design, if you try to work with AI, most of the AI people, okay, are coming from computing background. Okay, right? And this particular EDA and CAD requires electrical engineering background. Okay, so now what we say, now the time has come up. Actually the lectures I see in many of the top EDA companies are now actually working with AI. So now time has come that we had a course called CAD for VLSI or EDA for VLSI in our masters in many electrical engineering schools. Right now, I think we have to start one more course, which is for AI for CAD. Right, and this course AI for EDA or AI for CAD, and because what AI can do, AI can actually, as I said, that AI can actually give you that margin, okay, that margin where you require data-driven models, okay, that margin where you can have a predictive analytics of your design, right? Right, you can predict that means you can develop a predictive analytics of a design, and also now we are also using this for the test and fault awareness, fault resilience, because fault is so complex now. Okay, now so can we, and also I think very recently it is also being now done that the LLMs are using for RTL generation. You use the LLM codes for RTL generation, I think one of my friend, Professor Unshuman from ISI, okay, right, we are working with a common student, okay, for our PhD. And what we are trying to do, we are trying to generate an LLM verifier. So okay, LLM is generating a code, which will generate an RTL, a very log code system, very log code will generate an RTL. But how do we verify that? Okay, so we are also generating a sort of can we have again an automation on verification? So we are trying to automate on verification. Okay, right? And I was in DAC last year in San Francisco. We saw that okay, the first talk, okay, the keynote was from Microsoft, and the title was that AI for discovery. So which means that at this present point of time, AI is now helping on every point of discovery, starting from understanding data, okay, generating the preliminary design, understanding the scope, generating the preliminary design, generating the design, detailed design, verifying the design, okay, right, and maintenance. So all these steps you can suitably use AI, right, as it required, and all the major players have now started doing this. But having said so, you cannot be just closing your eyes and just think that AI will do everything. No, it's not like, because this is very domain intensive work. VLSI, EDA, CAD are very domain intensive work. So you have to be expertise in EDA, in CAD, in VLSI, and you will be the person, okay, you will be the person to try to find out that, okay, what are the areas where AI can be developed. And you also need to have the knowledge that AI can fail in some areas, right? And there either you develop AIs, that means correct the AI, or you need to develop some other strategies where AI fails. So these all the things will be done by the designers or engineers, right? But they will use an extra tool which is AI.
So autopilot is not possible.
Autopilot is not possible for designs.
Required.
Yeah, you can get an initial sketch, but you have to have a full control on that.
Final decision will be taken by human.
Perfect. Final decisions, iterations, what is required. Okay,
It's
because
just
AI is a cost. AI doesn't comes for free. AI comes with a cost. If you need to run an AI engine, it is a cost for you.
yes.
Okay, so you have to very judiciously understand where AI can help.
Yes, again, optimization. The designer has to make an optimized solution, have to come up with an optimized solution, when to use, where to use, and how much to use.
True. Perfect.
Yes.
Yeah.
So, since you are also connected with government policies and agencies, Higher Education Department of West Bengal, and you are connected to the all big university institute of this country. So, whatever initiatives are going on around, okay, so what do you think? You are in academics, in engineering technologies and teachings, research, in all of that. What gap you find out? What kind of gap is there which need to be addressed very soon to make the progress real, impactful progress in the field?
Yeah, this is a this is a $1,000,000 question, I will tell, because there are issues which we need to take care seriously, as you said. Okay, first issue is that we have to understand in academics that technology is changing very fast. Okay, right, and it is not possible for us to actually modulate or actually modify the syllabus in every year, because if you look into the VLSI technology only, right, and okay, from SOC which was just being spoke maybe 4 or 5 years ago, right, has now been converted to chiplet. So now we are discussing chiplets in our discussions, right? So it is moving very fast. So now what we need to do, we need to have the skill development. Okay, it's not that the skill development is only for students. Skill development is also for the trainers and for the faculty members of the institutes, and it is to be seriously taken and seriously considered, right? Don't make too many things, but what is going on, not okay, not actually, I'm not telling it that means in that way, but I think sometimes it is happening, too many things are going on. Let us faculty decide that, these are my 2-3 domains of expertise, and let me build on that. Okay, let me, because if you see the top, how a top institute becomes a top institute, because a top institute becomes a top institute because the student who graduates from the institute gets the training, which is as required to get him the job right now. Okay, so the training component of the student is actually marks that why the institute is good, because it trains the student at such a level that the student is just right to get a job, okay, job in the domain of his or her expertise. So this is very, I mean, don't get into too many expertise, which makes the life complex now, because now what is happening is that in Indian academy, too many things are being said. Let's try to decide that, okay, that each of the groups of the faculties will focus on two, okay, one, two, or maybe in a very extreme case, senior faculties may focus on three things. Okay, that's all, right? And try to develop a plan that, and need to work with the, need to have strong interaction with industries, startups, and some of the collaborators, either national or international, okay, so that we are always that seeing that what is going on in the technology space, because we have to learn, we have to we have to take some, we have to offer the students the things which are at present. Okay. Secondly, is in terms of high technology, I think that laboratory development is so important. Okay, it's not only teaching nowadays, right? It's I think the philosophy of our level of course where teaching was heavy, because at that point of time laboratory costs were pretty heavy and laboratories were not so abundant. But now I think there are lot of laboratories, lot of options of laboratories have come up, either virtual, that means, or hybrid, or physical. Lot of options have come up. Okay, so I think the students should be trained through doing the things much more than actually just trained to pass exam and get a grade. This we have to some way take care of, that learning is most important. What student learns, and the learning means that, what is learning? I tell my students class, what is learning? Learning means the knowledge comes in your thought process. Means that if I have taken an EDA course, and if I have given a design problem to my student, can the student visualize that, oh, these are the tasks I need to do? If the student can visualize these are the tasks I need to do, that is fine for me. Fine for me to get the course, because I am very much happy that the student have generated the thought process of the subject. So learning means actually you have generated a thought process on the subject, and that thought process will help you to solve a problem in your subject. Okay, so now you have to make your student to have that thought process, and thought process becomes much faster to the students if students do something and learns what was actually done correctly and what was done wrong. He or she will understand the things very fast. So we have to now split our course, I think, in a different way, in such a, there's some part of the course is very conceptual, which will take as a course, and some part of the course will be like that he or she will be given a task in constant touch with the faculty, and the faculty will help to make him or her understand that what was wrong in the task and what was right in the task, and then he will complete 4, 5, 6 tasks as required in a particular subject or a topic, and will learn that. I think that is the right approach what we need to take now, and we need to little bit modulate our curriculum and teaching practice in that way.
Okay. You have mentored a lot of students, and if what is your suggestion if a student want to pursue PhD, and they want to work in a domain which is a intersection of semiconductor, AI, quantum technologies? What should be your suggestion to students?
This is a fantastic domain what you said. Semiconductor, AI, and quantum, fantastic domain. But the thing is that to work on the semiconductor domain itself, right? Either you are going for EDA, where we are doing, right? You can go to fabrication also, process technology also you can do. You can also go to the device modeling, which is also one of the part. Also, you can go to architectural design. Okay, there are 4 or 5 blocks of, and you can also go to verification and testing. So there are 5, 6 blocks in this, right? That means if you want to go into VLSI, you have to have an idea of all these blocks at a baseline level. Okay, how that means, okay, CMOS transistor works. Okay, right. What are the architectural components of a memory and a processor? Okay, right. What are the basic EDA tools from where we can generate from your basic, okay, simple description to the RTL, right? And how we can write a test bench and we can verify the design. Okay. Then we also have to have a little bit idea of the technology in terms of processing. What are the processing technologies, right? How basic steps in fabrication, right? And you also have to know that how a particular design can be tested, verified. So these are the baselines you have to know in a VLSI, and then you accelerate in any one thing what you want. Okay? Maybe 1 or 2 things, maybe in 2 things. Maybe you can, if you are working on semiconductor devices, you can actually semiconductor device and process. You can look into these 2 areas, right? If you are doing for EDA, you can look into maybe EDA and verification. Fine, or you can go to architectural design and EDA. Perfect. So some of the things you have to be little bit specialized. For specialization, either you get the course from your industry, from your institute, or you get the course from the very professional course which are available. Okay, try to make a habit that you have to know the things. Okay, right, and try to do some good projects under supervision of your faculty members, right? Or do a project in another institute where we have a very good faculty who is expert in that domain. Okay, and try to get a maximum exposure, okay, to the work we do, because as I said, that you have to make a habit that you have to gather the knowledge more doing the things now, because the things are pretty okay, that means pretty complex. So unless you do the things only knowing the mathematics background, it might not be that way you can work with the things.
Okay. Finally, what excites you most about the next decade of computing and semiconductor innovation? And what do you see India making a global impact?
Yeah, we require more semiconductor companies coming in India. That's only the thing what we require now. We require more startups in semiconductor, okay, which will excite the students to focus on. Because at one point of time, I think I might be wrong, but what was my opinion is that I think for the last 2 years, semiconductor VLSI have again picked up among the students. But I think before that, 3-4 years, right, it was a little bit dilemma that whether the VLSI in academia is having that impact which it used to have. Okay, because so many software-driven the things in the software development technologies were coming up, right? People were thinking that hardware is becoming a very stagnant. Okay, but good thing is that we are now going through a technology node which is really fantastic, almost 1.5 nanometer technology node. Okay, which is really a challenge. Okay, we are having the LLM based EDAs which are coming up, right? AI driven verification which are coming up. We are having the chiplets, right, in terms of the packaging and process technology, which is fascinating. So there are a lot of and what I want to say, the silicon photonics. Silicon photonics, as AI is getting higher up, silicon photonics will have a boom because we have to have silicon photonics on chip, okay, to have this high speed communication and processing going on between the different components of your chip, right? And that is only possible if you have the optical interconnects. So those are the technologies which have suddenly got into place. Okay, right, and we have good number of manufacturing fabrication projects coming up in India. Okay, so this is now a fascinating and quantum computing also. So this is a fascinating time for the students to actually work on semiconductors. Okay, look into AI as a tool, right, and try to go into the design fabrication, verification of the semiconductors, and then maybe some of you will be motivated to actually look into the design of the qubits also. Okay, which will be the quantum computer. So that is, I think there is a there is a good amount of technology development has been done over the last 2-3 years due to AI and due to quantum on the semiconductor domain, and where new things have been come up in semiconductor, right? And right, that's fascinating, and that's why the students should get attracted in this domain. Yeah.
And what do you think? In coming decades, where would our country stand in all of these things? Where we can be?
That means if the government, my hope is always positive, right? Whatever negative thing happens, my hope is always positive in life, and about my country also, right? I love my country, I love my state. Okay, like many of us. Okay, so what I feel that, okay, if the government support goes on in this way, okay, right, if the government really supports the high technology domains, what is being done, going on the AI mission, the quantum mission, the semiconductor mission is going on, and we have a larger number of Indian origin entrepreneurs, okay, right, who will be maturing from startups to mid-level to MNCs, okay, and those we look forward to. We have the power of the Indian population. We have the knowledge of the very, very good Indian institutes and universities. We have a large number of student count in a okay, which has a very good that is in terms of age also we are very, very leading in terms of young age population. So I think we have a great hope. Only the thing is that, okay, we have to be little bit supportive to our country, because whatever it is our country. Okay, so that's the point to the all the young students, that we have lot of things. Obviously, we can do going out of the country. The lot of opportunities are there. Yeah, that means my motivation was always to learn the best, come to the country, right, and try to share your knowledge among your peers, among the students, and try to make our country, okay, more rich with our knowledge, with our collective knowledge. Okay, rather than thinking only about myself. Okay, that means about individual. You try to support our country, because it's our country, and we are the people who will be able to contribute to the country. And if we contribute seriously, right, our country will be one of the top countries in the world.
At the same time, I would say when 20 years back you were doing your PhD, it was like much more like small island. I mean,
Right.
the kind
Right.
of energy right now have in this country, and the kind of efforts are giving.
Perfect.
Obviously, that's because of government support. That was not there. So those who are entering now, they have a great hope. When you
True.
were in doing your PhD, that time, that kind of everything, you want to do something good, you have to leave the country. This
True.
kind of, it's very
True.
demoralizing for students or
True.
youngsters. And
True.
now you have faced that thing. Now you are trying to work in staying in the country. So that's a great support, I would say. Not only you, many people are like that. So, and companies are coming now. I mean, I think days are much better compared to that time, isn't it?
Perfect. Lot of startups have opened up. They are doing pretty good. Okay, lot of people in India have understood that a startup is one of the thing, okay, which we should do. We shouldn't go for job. I also support some of the startups. Okay, in their thought process. So I am very, very open to startups. Right. I just try to. That means okay. That means if somebody is okay, someone is doing something in India. Okay, right. Any institute, any startup, right. According to my limited capacity, whatever I can help, I do it. Okay, so I think the thing is changing in India. Government is giving an active support to industry, academia collaboration, which was not that level, as you rightly said, at that level when we are doing masters or our PhD programs. And now it is a very mandate that industries and academia has to work together. So the students and the faculty members and the researchers and the industry experts should now work together, right, and have that means and take the best of their abilities to to make our country as a very successful country in technology.
So these are questions from my side. Have I missed anything and you have something in your mind to share with the viewers?
No, I think I have shared. The questions were pretty good, and they were very what to okay, to what is required at this point of time. I thank you also, okay, to plan this question and offer it to me, right. So I am fine with the questions. If there is anything more from the audience, I will be fine to answer. Yeah.
I think to some extent, the kind of depth, technical knowledge you have shared, I think many people will rewatch the video and try to understand, and that will give them opportunity. Honestly, not the kind of quantum mechanics, quantum computing, everything. Just don't let it be a flyer only in LinkedIn. If we get to know what is inside, we need to understand, attend some conference or something. And today you are here, you have shared so many things. In fact, I think I would start studying something, some more thing, because that's
So
not
good.
my. But interest is there. Why it's getting so much traction? Why it's so technology for the future? Why it's people are telling so? So I mean, it's a very eye-opening session. So I don't know whether question will come, but later on keeps on question
Sure.
keeps on coming.
Sure.
So
Sure. Thank you.
I
I'm very happy. Yeah. Thanks for hosting me.
Oh, thank you. So, viewers, we are done for our today's episode, and this session has been an amazing session with Amlanda. Thank you for watching up to this point. Don't forget to like, share, and subscribe to our channel, and don't forget to share TSP videos with in your circle, in your domain. Thank you very much staying up to this point. Thank you, and bye for today.
Thank you all. Thank you.